Hi everybody. Well, as you can see, I have a little bit different setup today. Um, had some issues of a technological nature, so that's all right. We will just go on. Please let me know in the chat if you have issues with this, like you can't hear me or something's not working again. Hey Daisy. And I will try to get it worked out. Hopefully we'll get through this today okay. As usual, you can say hi in the chat. You can ask questions in the Discord, whatever works best for you. So we'll wait a minute or so for whoever wants to join us, and then we will get started. Hey, Alyssa. The graphs you mean for the lab? Let me take a look there, just so I'm sure we're looking at the same thing here. Let me see if I can bring this up on the screen. It might take a minute. So there's a question about the graphs on the lab. I assume that's speaking about the lab. So I thought I loaded it. Oh, right here. Okay. Yeah, so the fat extraction chart, I'm going to talk about that too. It's not loading right now, but I'll get it up eventually. Let's take a look at this one first. So I see what you mean. So like these kinds of graphs. So what does that mean? So this is something that you probably want to look up, I would say. And the reason for that is that the relationship makes sense that we talked about last time. So if you think about like, okay, here are your axes. So pressure and volume. We should have just done one of these together. So you've got pressure and volume. So what happens as the pressure goes up? What happens to the volume? As the volume goes up, what happens to the pressure? So that's the kind of graph that we want to see. Now, for pressure and volume, the relationship is not linear. So the relationship between pressure and volume ends up looking something like this. So as pressure goes up, volume goes down. As volume goes up, pressure goes down, but in a non-linear fashion. And that's because of that inversely proportional relationship, right? You can't divide by 0, so an inverse function, you end up making, I think that's a hyperbola. And then the other graphs are the same idea. So if that's not clear to you, like you can just look those up and then put those here as a reference. People who are more visual in the way they like to learn about and think about these kinds of things, it can be really helpful to just remember a picture of a graph and then use that to actually figure out like what the relationship is. Like what happens if I reduce pressure, what happens if I increase pressure. So that's why it can be useful to have those graphs right there. Try to load the fat extraction thing again. All right, give me a minute here. Okay, there we go. So, get out of the Prelab here. all right, this is what I thought you meant from the graph. So this is the same idea. This is a gas graph um, of what happens as you change these things. Now, we will do this in lab next week. And if I think about it, if you want, I can probably set up a camera and just record it for you. So those of you who are supposed to do it this week, or we're supposed to do it this week, you can still see what it looks like in our lab. But you can also just, I mean, these are common demos. So you can watch the videos that are linked here, talk about the observations, what happened, what's held constant, what's changed, and then graph that. So like at this temperature you have this, at this temperature you have this, at this temperature you have this, and you just kind of set up your axes however you want. So for the fat extraction part, the idea here is you're using some potato chips which have a lot of fat, and fat is non-polar. We'll be talking more about polar and non-polar interactions today. But the nonpolar fat is going to be more soluble in a nonpolar solvent. So the idea here is you have some chips, and you are weighing the chips and then getting some information about the mass percent of the chips, and then you are extracting them with some solvent. So this, one other thing that might help, this is not meant to be a standalone document. This is supposed to be your data sheet. You also need to be looking at the actual procedure document that's linked in Blackboard. So even though this is the online one, the only thing that really changes is that your data are given here instead of you finding them. So if you actually did the experiment, you would be finding these numbers and putting them here. Because it's online, these numbers are being given to you. So the only difference for like the people doing it next week is you won't be using these numbers, you'll be getting your own numbers. But with these numbers and the instructions, you should be able to figure out the rest of the information. So for example, after you extract the fat, and again, you got to read the instructions to see kind of what that means, you have now a beaker with some fat in it. So the difference between the mass of the beaker and the mass of the beaker with the fat, in both cases, is the experimental mass of fat. Right? So how much you calculated. And for more information on what's exactly supposed to go here, go back to the instructions, and it should walk you through there. Of course, if you still have questions, let me know. But these are all the numbers that you would have gotten were you to actually do the experiment. So by just being given those numbers, you should have everything you need to complete that. Yeah, you should fill in yours and the partners. Yeah, we can look at the gas laws part too. So the reason that you're doing both of them, normally like you would be doing your chips, your partners would be doing your partner's chips, and just so you had more data. Because what happens in this lab, whoops, it's not showing anymore. What happens in this lab is sometimes there's some pretty wild variation in data. Sometimes stuff just doesn't work. So it's always good to have two data sets to compare against. So yeah, you want to look at both yours and your partner's chips so that you can have something to compare about and think about it that way. Let's go back up to the gas laws part. Oh, that's in the other thing. This part, right? Gas laws in action. So yes, what questions do you have about that part? Yeah, the bubbles in the scuba diver. Let's take a look at that one. So first of all, there's a little bit of a typo here, so that should be they. The bubbles exhaled by a scuba diver grow as they approach the surface of the ocean. So You exhale a bubble way down underwater, and then as it comes up, it gets bigger and bigger and bigger and bigger. Neither. I think the point of this, like the bubbles that are exhaled. So like the scuba diver's breathing and then just blowing bubbles, like when you put your face in the water and you blow bubbles. Those bubbles are the ones that you're focused. The air inside those bubbles is what we're talking about here. So in that case, we can say that the amount of gas and the temperature are held constant. Of course, there's going to be temperature variation in the ocean, but that's not really what's causing the major effect here. The main thing here is the pressure is decreasing as the bubbles rise to the surface, and so that causes the volume to increase. So does that make sense? The pressure is not increasing, the pressure is decreasing because there's the ocean, the water exerts less pressure the further toward the surface you go. So as you go deeper, you have more water pressure pushing on everything. And then as the bubbles approach the surface, the pressure decreases. And so the bubbles can get bigger. Is that, or did you just mean where is the pressure increasing in all of these? Yeah, that's fine. That is always a problem with these types of examples is they assume a certain amount of experience with these various things that people may or may not have any idea what's going on. Like maybe you've never cooked a turkey with a turkey syringe thermometer that pops out, which actually is not. Now that I'm looking at that, we should look this up. But I don't think a turkey syringe thermometer has anything to do with gas. I think it's a temperature actuated thing. Let me. We should look that up because I think what happens is there's metals that as they get to a particular temperature, the metal changes its shape and that causes like a spring to pop out. So I think the idea here, if we're talking about gases, whoever I didn't write this example, but I think the idea is that like the steam produced inside the turkey causes an increase in pressure which pushes out a plunger. So that would be like a volume, a pressure, increased pressure leads, or sorry, a that you increase the pressure and you'd push that thing out. But that's not really how those work. I'm pretty sure those are metallic thermocouples, and when the metal gets to a certain temperature, it slightly changes its shape and causes a spring to pop out, because I think those are spring loaded. But we could look that up and see. Any of these other ones? We should look. Maybe some other ones are wrong too. Or you know what? The other thing they might have been thinking about here is about if you increase the temperature of a gas at constant pressure, you're going to increase the volume. So if there's a gas inside the syringe and then the turkey temperature increases the temperature of the gas, and that kind of pushes the syringe out. So it increases the volume of the syringe. That would make sense from a gas loss perspective. But again, I don't think that's how the turkey thermometers work. All right, let's take a look at intermolecular forces. So Let's take a look at this word first, intermolecular forces. You've probably heard this type of a prefix before, but you can have inter something, you can have intra something. Intra, which means like within the same thing, and inter means between different things. So intramolecular forces are bonds. That's what we called bonds. We had polar ionic bonds, we had nonpolar covalent bonds, and then we had polar covalent bonds. We've talked about those types of interactions. So now we're talking about the interactions between different molecules. So how does one molecule of a substance interact with another molecule of a substance? Or how does a molecule of one substance interact with a molecule of a different substance? Or atoms, if we're going down to the atoms. So this is a really, really important part of chemistry because it explains a lot of behavior. And if you are trying to like determine why don't these things mix, or why does this thing have a higher boiling point than this other thing, the answer is generally intermolecular forces. So what we're going to do is just kind of go through the basic categories of these forces, talk about how they work, what they are, and how they are, and what their strength is relative to each other. And then we'll use that to judge some of these properties. All right. So the first weakest type of intermolecular force are the dispersion forces. These go by a few different names. So sometimes they're called London dispersion forces. Sometimes they're called induced dipole forces. And sometimes just dispersion forces. And these are generally the most important forces between nonpolar molecules. Sorry, I'm trying to write really small, but that says most important between nonpolar molecules. And the reason that's important distinction is because of this last sentence here. London dispersion forces are present in all molecules. So all molecules will have these types of forces, but polar molecules have other stronger forces that we're going to talk about in a minute. And nonpolar molecules only have these types of forces, these dispersion forces. So this is how they work. All molecules or atoms that have electrons, you can imagine that the electrons are moving around the molecule kind of randomly. And at any given moment, they may be more on one side than the other. So we're just talking about momentarily. Like on average, they're all over, but momentarily they could be stuck in one spot. And so at that exact moment, if we took a quick snapshot, there would be a negative charge on this side of the molecule and a positive charge on that side of the molecule. Now you can't really take a snapshot of electrons because of quantum mechanical uncertainty, but that's a whole other thing. So let's just pretend that it helps explain anyway. So at that exact moment, there's a little bit more negative on this side, a little bit more positive on this side. And then that actually causes more dipoles on the other surrounding molecules. So if this side is now a little bit more positive, then it's going to attract the electrons from this molecule that's right next to it, and then it's going to attract the molecule right next to it, and so on, and there will be this cascade of dipoles happening there. And so that's where you get this induced dipole or dispersion or London dispersion forces. Yeah, the electrons, because the electrons are negative. So when they're over on one side, it's a little bit more negative on that side. All right. So these forces, the strength of these forces, yeah, exactly, Jennifer. They form kind of a line of molecules. So all of these things are going to like cause them to line up and attract each other. And the strength of these forces is determined by two things. Most importantly, the atomic mass. So big molecules with lots of electrons have stronger dispersion forces than small molecules with fewer electrons. Kind of makes sense. The more electrons you have, the more of this kind of lining up you can do. And then secondly, by shape. So if you have long linear molecules like this, they can line up very, very well with each other and kind of pack nice and tightly. Those are going to have nice and strong forces, versus ones that are maybe shaped like this that can't quite get in at each other quite as well. And so they're not going to pack quite as tightly, and those forces won't be quite as strong. But the most importantly is generally the atomic mass. So if you think about the alkanes, the hydrocarbons, I think, do I have that down here somewhere? I can't remember if I put it on this one or not. I guess not. We can look at boiling points as a way of kind of measuring these forces. So if you think about molecules made only from carbon and hydrogen, the lightest ones, those are totally nonpolar. So those are all dispersion forces. And the lightest examples of those are methane, ethane, propane, butane. Those are all gases. So methane is like natural gas. And then as you get into the kind of mid-range, you get pentane and hexane and heptane, octane. Those are liquids, like gasoline is mostly octane. So now you have liquids because the forces are now getting strong enough that these molecules can hold together in the liquid. And then as you get really, really big ones, you can actually start to get solids and things like waxes that are these really long chain non-polar molecules that have enough dispersion forces to pack together. Things like fats are a good example of that too. Saturated fats have these long chains that can pack together very tightly. So things like butter, lard, animal fats that are solid at room temperature, coconut oil. And then the unsaturated fats that aren't straight, that have like twisty chains, can't pack together quite as tightly. So those are the fats that would be in oils, canola oil, olive oil, stuff like that. So that's your dispersion forces. So we are determining their strength by the size and the shape. And they're most important when we can determine that a molecule is totally nonpolar and doesn't have any kind of polar interactions. All right. So the other side of that is the dipole forces, which are between two polar molecules. So let's look at, for example, CO. We've got a polar covalent bond here, which we talked about in the last chapter, that oxygen is more or not last chapter, a few chapters ago, oxygen's more electronegative than carbon, pulls the electrons toward itself, and so you have a partial negative on the oxygen and a partial positive on the carbon. So the oxygen's a little bit negative, carbon's a little bit positive. And that will allow it to attract another CO molecule that also has a partial positive and a partial negative. So how do you know which one is which? Remember that we look at the electronegativity. Does it only attract the same molecule? No. They can attract different molecules, like in a solution or something like that as well. Usually when we talk about, at least at first, when we talk about these examples, we're focused on the forces between molecules of the same compound. But if you had a mixture, it could be between molecules in the mixture also. All right. And then we have a very special case. This is technically, I mean, it is a type of dipole force, although electronically it's a little bit different. But in a couple special cases, the dipole is so strong that it can do this extra thing called hydrogen bonding. And this is a really confusing term. So let's make a little star and remind ourselves that this is indeed confusing. Whoa, what's happening? Okay. Is that writing coming up? Yeah, okay. That is confusing. Why is it confusing? Because it uses this term bonding. But it's not bonding. It's not a covalent bond. It's an intermolecular force. It's a force it's an attractive force between two separate molecules, not a bond within a molecule like we talked about last time, like a covalent bond. Well, not last time, several times ago. So this happens whenever one of the atoms that's involved in the interaction here is an N, an O, or an F. You may recognize or remember those as the most electronegative elements. So when there's a hydrogen that's connected to one of those and interacting with another one, so like here you have a nitrogen hydrogen bond that is attracting or being attractive with a negatively charged oxygen on the other side, then you can have this thing called hydrogen bonding. And hydrogen bonding is a stronger interaction than the dipolar interactions we just talked about over here. So when you can have nitrogen, oxygen, or fluorine involved in this thing, you have a stronger interaction. And this is an extremely important interaction because it is what holds DNA, RNA, and proteins together. So if you've taken some biology or physiology and you know there's like the two strands of DNA with the base pairs here, right? And they line right up, and those are hydrogen bonds that hold those things together. That's also what holds water together, another OH compound, and gives it all its special properties, like that it can be a liquid at really high temperature compared to most other substances. And so on. And then the last couple, or I guess the last one here, I'm going to put kind of parentheses around it, because I don't want you to get confused about this type of interaction. So technically the strongest force here is when you have a fully charged ion, like a chloride ion or a sodium ion, that is then interacting with some dipolar molecule. So if you have water molecules, in this example, this is how sodium chloride dissolves in water. The sodium and the chloride are broken apart, and water molecules surround each. The positive part of the water molecules, the hydrogen, would point toward the chloride, and the negative part, the partially negative part, the oxygen, would point toward the sodium. And these are shown as like a circle, but really it would be a sphere all the way around the ion. And so when you have that ion, you have a little bit of a stronger force, but also ionic bonds are stronger. Those are not really an intermolecular force anymore. So they're not really in the same category. The main three things, or the main three categories of intermolecular forces that you need to know in this class are the dispersion forces, dipole forces, and hydrogen bonding. All right. So we said that those contribute to a bunch of properties. And these are some of the properties that are controlled by intermolecular forces. So viscosity is something kind of like syrupy and doesn't flow very quickly, or does it flow very easily? Surface tension. Liquids will always try to have the least surface area possible. So is it going to really like bead up, or is it going to spread out? And then these kind of cohesion, adhesion. So, you talk about adhesives, like chemicals that can make things stick to each other. These are all based on intermolecular forces generally, not chemical bonding or chemical reactions. And then boiling point is the big one, because that's so easily measurable. If you can determine the boiling point, or if you can look up the boiling point, you can have a really good sense of how strong the intermolecular forces are. Think about what boiling means. We don't break apart molecules into their atoms when we boil. We just break the molecules apart from each other. So like with water, when you turn water into water vapor, you're separating the water molecules from each other. And so you have to break the intermolecular forces to do that. So the energy that it takes to do that is proportional to the strength of those intermolecular forces. And so boiling point makes a really, really nice kind of shorthand for intermolecular forces, because you can always look it up, or you can measure it, you can know the boiling points. Melting point also involves intermolecular forces, but it's a little bit trickier because it doesn't track exactly with the strength of the forces. The strongest forces don't always give you the highest melting points. But that's because there's other stuff involved there. We don't have to worry so much about that. But boiling point is the big one that we're going to talk about. All right. So let's look at an example. So octane is found in gasoline, and propane is used for, I mean, lots of things, but let's say a grill, the tank. So at room temperature, octane, we could also have said, stoves or electricity in some places, or lots of things. At room temperature, octane is a liquid. And this pen is not tracking nicely right now. Whereas propane is a gas. And if we look at the structures of those, propane is 3 carbons and 8 hydrogens. Whereas octane is 8 carbons and 18 hydrogens. I'm actually not even going to draw them all in, but you can just assume these things are hydrogens. So with that much larger molecule, there's a lot more electrons and a lot more surface area for dispersion forces. And we know that it has to be only dispersion forces because carbon-carbon and carbon-hydrogen bonds are nonpolar. All right, so here's a nice little flow chart, how you decide what types of intermolecular forces are present. Well, what's the strongest forces? Right. So first, are there ions? Let's say no. Are any of the molecules polar? Let's say yes. Are there H atoms that are bonded to NO and F? Yes. Then your strongest intermolecular force is hydrogen bonding. If you didn't have those hydrogen bonded to NO or F, you'd have dipole forces. And if you said there was no polarity at all, then you can only have dispersion forces. All right, questions about that classification? All right. So let's take a look now to kind of sum this up. You can go through those previous examples, I think. Certainly let me know if you have questions or if it doesn't make sense. But I wanted to look at specific examples of where we would see these and how we could guess the most important type of intermolecular forces. So I'm gonna just draw the structure. I know you can do Lewis dot structures at this point. I'm just gonna draw these for you. So CH3CN. You got the 3 H's on the C. CN. That is covalent. It has a nice polar bond right there between the C and the N. And it is actually a polar molecule. Although as we would deal with bigger and bigger molecules, like nucleic acids, proteins, and things like that, the whole molecule being polar will be less important, and we'll care more about areas of the molecule. I mean, not always, but it's hard to tell if something is going to be polar or not if you don't know the structure. So generally, yes, you don't necessarily need to draw it if you know it, if it's something that we've talked about a lot. But if you don't, then you should draw the Lewis structure so you can tell if it's going to be polar or not. In this case, there cannot be hydrogen bonding because there's no H's that are connected to NO's and F's. And so the strongest intermolecular forces here are the dipole forces. So the dipolar forces. The reason I say strongest there is, remember, everything has dispersion forces. So in this case, the most important, strongest force for this molecule is the dipole force. Yep, we'll keep going. So let's look at HF. There's our Lewis structure. That one is also covalent. That HF bond, yes, is very polar. So yes, it is a polar molecule because that's the whole molecule. Hydrogen bonding, this time we say yes because that hydrogen is connected to a fluorine, right? So that fulfills that condition, a hydrogen connected to NO or F. And so we would expect the strongest force here to be hydrogen bond or hydrogen bonding. All right, NH3. This is going to be, we've seen these types of compounds before. It's like a trigonal pyramidal structure, so all the H's are kind of down below the nitrogen. You can think of it that way. That is covalent. That does have polar bonds. It is a polar molecule. And then again, this time we can say yes to hydrogen bonding because the NO-F condition is met. We have NO or F bonded to hydrogen. And that is therefore hydrogen bonding. Will you have the summary available, or should you memorize it for the exam? You should know it. You should know those three terms. You should know dispersion forces, dipolar forces, and hydrogen bonding, and how to do a table like this. You would have electronegativity values available to you, so you can use that to judge the polarity or whether or not it's polar, but you would not have the definitions. All right. I'll leave the last three for you to at least try. We can always come back and do these again on Tuesday if you want to go back to it, or if I get a lot of questions this weekend, if you can't tell, let me know, and we'll talk about it some more. But I do want to give you a chance to try some of these as well. For these last ones that talk about some other things, about viscosity, surface tension, melting point, this is all stuff that you should look up. This is not stuff that I would expect you to just know. It's also not going to come up a whole lot in this class. It's more just for your own interest, but it is interesting. Let's look at another example. I want to look at 51 here. So based on the intermolecular forces present, predict the relative boiling points of each of the substances below. Arrange each series of substances in order of increasing boiling point. State your reasons for the order you use. There's only one set of substances here. I don't know. I think I cut that down from what it was before. All right, so this is a really, really common type of a question when we talk about intermolecular forces. Can you arrange these substances in order of boiling point when all you know is their structures? So we don't know their boiling points. How do we figure that out? Well, we use the idea that boiling points, relative boiling points, are proportional to strength of intermolecular forces. So whichever compounds are going to have the strongest forces will have the highest boiling points. All right, so let's look at our structures here. We've got propane. We drew that one before. Okay. We've got dimethyl ether over here. And then we have ethanol over here. And I drew these all with straight 90-degree bonds, but the fact is that all of these should be tetrahedral, so the bond angles would really be zigzagged, about 110 degrees back and forth. So we can think about that part as well. Okay, so how do we figure this out? Well, whenever we are trying to judge relative boiling points, as I said, What we're really doing is we're judging the strength of intermolecular forces. And when we're judging the strength of intermolecular forces, there's generally two things that you want to look at. So first is going to be the type of the force. Those three categories of forces, dispersion forces, dipole forces, hydrogen bonding, have big differences in their strengths. So if we have something that does hydrogen bonding, we're almost always going to rank that in boiling point and intermolecular force strength above something that doesn't do hydrogen bonding. If it happens that all of them are about the same types of forces, so it's a whole bunch of compounds that have, like all three compounds have, let's say, hydrogen bonding, then how do we rank them? Well, then the second step is to look at the size, because the bigger molecules will have more dispersion forces and therefore higher boiling points. But in this case, if we look at these three compounds, these are all about the same size. They've all got about the same molecular weight. So that means that we can't really compare their size because their size is pretty comparable. If not identical, at least pretty comparable. So what we have to look at is the types of forces present here. For propane, we can say that we have nothing because the computer got angry. Okay, there we go. For propane, we're only really going to have dispersion forces. For dimethyl ether, we now have some polar bonds because of the CO. CO is a polar bond. So we can have some dipole forces in there. And then for ethanol, we have the magic OH bond, this interaction between hydrogen and NO or F. And so there we go. We determined our difference in intermolecular forces, and therefore we can determine our difference in boiling point. So we would expect ethanol to have the highest boiling point, dimethyl ether to be second, and propane to be third. And in fact, that is true. Ethanol's boiling point is, I think, 78 C. Dimethyl ether is like 30-ish. And propane is really, really low. It's a gas at room temperature. So those intermolecular forces nicely explain the boiling points that we see. Okay, so the last thing I want to talk about when we are, and this we already kind of talked about this, we're just going to put a new word on it. When we're talking about dispersion forces, think back to what a dispersion force is. It's those electrons moving off to one side or another. So the more easily they can do that, the stronger that force becomes, and that's called polarizability. This word here, polarizability. So how easy is it to move those electrons to one side or the other? The bigger the atom or the molecule, generally the more polarizable it is. So the more that those electrons can be pulled around, and so you have higher boiling points, stronger intermolecular forces for bigger molecules than for smaller ones. So in this example, you have iodine, bromine, and chlorine, I2Br2Cl2. Those are all nonpolar because they're just the same atom on two sides of a bond. But iodine's a solid, bromine's a liquid, and chlorine is a gas. So that tells you something at room temperature. That tells you something about their intermolecular forces. That iodine is going to have the strongest forces, bromine the next strongest, and chlorine the weakest. And that's directly proportional then to their sizes. So iodine is the largest with the most electrons, therefore the most polarizable and the strongest dispersion forces. Bromine next, and then chlorine's the weakest. So then if we move on to this example 53, we now have an example, and this is the last thing we'll do tonight, where it gets a little bit trickier because we have two molecules, methane and octane, which are both primarily controlled by dispersion forces. And then we have two molecules, ethanol and water, that are primarily controlled by hydrogen bonding forces. But we want to rank all four of them from lowest to highest boiling point. So why don't you give it a try with those? And if you feel brave and you want to give it a guess, put it in the chat, and then we'll see how it goes. Oh, good question, Alyssa. So what was blank here? In terms of intermolecular forces, these are all dispersion forces because they're all nonpolar. Or London dispersion forces, or London forces, sometimes they're called. Is anybody going to answer, or just wait? You're just waiting for me to talk about it? For 53. Oh, you're so close. You're so close. This is... I'm actually looking up one of these because I don't... Yeah. So this one is like purposefully extra difficult. I would be surprised if anybody could do this. And so it's almost not really a fair question because, yes, bigger things are more polarizable, but also it really depends on the types of forces. So you would think here, okay, methane and octane, oops, sorry, have those weaker dispersion forces, and ethanol and water have hydrogen bonding. So a good first way of looking at it would be to say, like, okay, well, let's look within the categories first. So within this category, we've got methane and octane. Octane's clearly bigger, more polarizable, more electrons. So octane's going to have a higher boiling point than methane. And you'd be totally right there. Then you jump over here and you go, okay, well, ethanol and water, they're both hydrogen bonding. Ethanol is a little bigger, so we would expect that to be higher boiling than water. But guess what? It's not. Ethanol boiling point is 78 degrees C, and water's boiling point is 100 degrees C. And this is because it's not because any of these are weird or anything is going on weird over here. It's because water is weird. Water is this very, very strange, completely unique chemical that has these properties that nothing else has. So it has a much higher boiling point than anything else, even close to its size. It's a small, really small molecule with a really, really high boiling point. Yeah. So methane, octane, water, ethanol totally seems like the logical way for this to go, and it turns out to be wrong. And we'll talk about why that doesn't work in this case. So if we actually look up these boiling points, octane is 126 degrees C boiling point. And then methane is super, super low. I'm just going to look it up. So negative 161.5. So we could use polarizability pretty well to determine that octane's going to be more, it's going to be higher boiling than methane. That's great. And we could use the idea of hydrogen bonding to see that these are going to be in general higher than a comparably sized molecule. So keep in mind, water and methane are the same size, basically. So the big difference here is from their difference in forces, not from the size effect. And so water turns out to be really special because it has those two hydrogens per oxygen. It can make a much tighter water network. You can look at some pictures of this where water molecules are all kind of bound together than other polar molecules like ethanol. So it turns out that ethanol, that extra size, actually doesn't help it. That C2H5 part of ethanol is nonpolar and kind of ends up getting in the way of the rest of it. Yeah, so in this example, actually octane has the highest boiling point, right? Which you might not expect, except that it just ends up being so big that that polarizability and those electrons become more important than the forces even in water and ethanol. So that's what's happening here. This is kind of a trick question. So we'll just put like a sad face because nobody likes those. But it is good to know that sometimes things don't work out the way you'd expect it, and you can go through your logic, but ultimately you have to go with the measurements, even if it doesn't fit your rules. Yeah. But the nice thing about this is information that can be looked up. So when you're doing your master in chemistry and it's asking you to compare one type of a molecule with another, compare the intermolecular forces, you can look up the boiling points of those molecules, not just so you get the answer right, but you can guess based on the structure, and you can say, okay, I think based on the structure that these are going to be ranked in this way. And then you can actually look it up to confirm that, because you can look up boiling points. Now, nothing in mastering chemistry or on exam should ever be like this, because obviously this goes against our expectations, and that's not usually how we do things. But if you do need to find out this information, you can look up boiling points. All right. So before we go, one last thing about the labs this week. So originally, the idea was to have the in-lab part be the fat extraction, and then outside of lab, the virtual lab part would be the gas laws. But because we're going virtual last week anyway, and it's all kind of together, I just lumped that together. So both of these labs will be due together either this week or next week. So even if you had them, if you were supposed to have lab this week, there isn't a separate virtual lab for you next week. You could just kind of do half and half of the assignment. So the entire lab will be due, I'll move the date back, the entire lab will be due not this weekend Sunday, but next week Sunday. So that way you can do like half the fat extraction now, and then the virtual lab next time. And then for the section B04, hopefully we can still get on campus next week. Although with the way things have been going, it's like new cases every day on campus. So I wouldn't be surprised if we are called off again next week, but we will see. I hope that you all stay healthy and take care of yourselves and take care of each other. Any last questions before we go tonight? All right, I will take that as a no, but of course you can always send me questions if you have them. And yeah, have a good weekend. Have a good night.